Hello, this is video number 24. And what are we going to talk about now? Let's talk about the put operation, OPR for short, in specifically a BST dictionary. Kind of blurring the line here a little bit, just a little bit. We're going to implement our dictionary, our first official dictionary, as a binary search tree, but those two are not necessarily so intricately linked. A binary search tree is a particular thing. Go to the left, it's smaller. Go to the right, it's larger. A dictionary is a specific thing. Send in a key, get back a value. But I'm going to blur the line a little bit because we are actually using our BST to implement a dictionary, and I'm repeating myself now. So let's look at the put operation, and let's say, this is all going to be example. Let's say the data that we're inserting, the key is the name of an animal, and the value has a bunch of stuff about that animal, maybe a picture and all kinds of characteristics, history of what? History of the animal. And I'm going to insert cow and pig and dog. And I don't want to write out a bunch of information. So here, this is a cow with horns. This is a pig with a curly tail. Fix the horns over here. I should have drawn the pictures in advance. And this is a dog with pointy ears. There. This is going to be an image database, an image dictionary, where we insert these gigantic JPEG images. And the key is going to be the actual name of the animal that we send in. So the keys, why do I keep saying what the keys are? What difference does it make? The keys are actually what determines where these things will go in our binary search tree. That's what we're comparing to decide whether we need to go to the left, go to the right, whatever. And I'm going to do this, given the data there, I'm going to do this by cases, because there are different things that can come up. Case number 1, new root. In other words, this is the very first thing that's being inserted. There's nothing there. So the root, let's see, before and after. The root at that point would be a single external node, a little square. The after picture, using my example data, well, the root won't be just a single little square anymore. The root will be the cow. So root will point at a node that has key value cow, which I am making part of the value. Remember, that's not necessarily the case, but it could be. Key value cow and the picture, all that stuff is in there in the node. There, that represents the picture. But it also has, inside this node, all of this together is the data, the cow and the picture and all that stuff. That's the data, but it's got 2 external nodes hanging off the bottom. Okay? So here's before and after. Before, there's nothing. The root is a single, remember, a binary search tree, even when it's empty, it's viewed to be a single external node. We replace that with an internal node and swing off 2 kids that are external nodes left and right, like so. So far, so good. Okay, how about case number 2? And which one is it going to be? I spy, we're going to need a new right child. New right child. I'm predicting what's going to happen. Here's the before, and I'm going to cheat and say same as previous after. Same as after. I guess I better draw a line or these are going to get confused, aren't they? That is the same as the before picture here. And I'm inserting pig. Let's do the comparison. We're comparing only the keys. We don't even look at the pictures. Pig is greater than cow. So we look and there's no right child. So this becomes the right child. So the after picture There's not going to be anywhere near enough room on this board. The root, I'm going to quit doing the picture. The root points at the node that has the cow information in it. Left and right child. Except that even though the left child will still be an external node, the right child, this external node, will be replaced with a new node that has the pig in it. So you can visualize a picture of a pig down there below pig and two external nodes hanging off the bottom. Since I've already hopelessly butchered the board and all these different kind of segments here, I'm going to do the same thing for case 3. Let's see. I think this will do it, won't it? If I set this up correctly. Yeah, when we insert dog, this is going to be a new left child. And I've got the same before. Well, not the same before. I'm sorry. Same as most recent after. You could write that down. I didn't have room. Same as the most recent after. Here's my before picture for this one. And here we go. We insert dog. Dog is greater than cow. We're only comparing the keys. Dog is less than pig, so it becomes the new left child of pig. Root. This is the after picture, by the way. So we'll have root. Cow is at the root. Whatever the first thing inserted is permanently the root. You'll remember that. There's no left child still. The right child, these are getting smaller and smaller as we get further down the board. The right child is pig. And when we compared, dog was greater than cow, less than pig. So dog is the left child of pig. Dog. Tiny little squares, external nodes. And the right child of pig is still external. There. Cow, pig, dog. All in our binary search tree, implementing a dictionary. Now we could look up pigs. You know what? There's actually one more case. This board will be completely full. We'll set a new record. For no new node. Where did that come from? Well, let's insert pig again. Maybe the data had a duplicate. It doesn't mean that it's necessarily duplicate value. This could be a pig facing the other direction. But if it's got the same key, we disallow it. So when we try to insert P, it just fails. Insert P, is that what I said? Insert pig. When we try to insert pig, here we go. Cow, a pig is greater than cow. Pig equals pig. So we return false at that point and don't even go all the rest of the way down the tree. Okay, what have we learned from this? Well, I'm going to allocate new space. The data is all inserted. I don't need to look at the data anymore. But I do want to make a couple of observations. Observation number 1. In each successful put, an external node replaced by an internal node with 2 children. I think we visited that before. Here it is. We've seen it in action. That says put, and I intended to double underline. An external node is replaced by an internal node with 2 external kids, heavily abbreviated. It's so abbreviated, I'll read it back in case you can't read it on the board. And each successful put operation in our binary search tree that's implementing a dictionary. And each successful put, an external node, one of the little squares, is replaced by an internal node with 2 external kids. I don't know if I believe that. Let's check. here's the very first case, absolutely empty tree. The root is nothing but an external node. We rip out that little external node, and in its place we put an internal node that says cow, facing in the other direction, with two kids, left and right, that are external nodes. What about the new right child? Before is the same as this, but look what we do. We replace that right child, that external node, with an internal node with two external kids. What about a new left child? Here's the before picture for that. We replace, in this case, the left child with a pointer to an internal node that has dog, the dog value in it, with two external kids. So that appears to be correct based on the data that we have available to us at this point. And in fact, yes, it's always going to be like that. Two is actually a bigger, more important observation to us. We're doing more work than we have to do. The observation number 2 is that the external node is empty, doesn't have any data in it. And that's kind of standard for this kind of application. It's not for every application for a binary search tree, so we got to be careful making these extremely broad generalizations. But in our case, the external node is really just a placeholder. That's where a new node is going to go if I have to go to the left or right off the bottom of the tree. The external node is empty, thus, that must mean something important is coming. The external node is empty, thus, it's a waste of memory space. It's a waste of memory space for us to dynamically allocate storage for these little squares down here that don't even have anything in them. We certainly don't want to set up a separate node structure called external node and dynamically allocate those and have pointers to them in the left and right and all that stuff. So what can we do? Oh no, solution. Let a 0 pointer stand in for an external node. Now that might not make any sense, but I'm going to read it back anyway. Let a 0 pointer, whenever we see a 0 pointer that should be pointing to a node in our tree, if we run into a 0, we say, we've reached an external node. Why would we even want to view it that way? Well, a lot of the algorithms, particularly the recursive algorithms that go up and down trees and everything, they're going to be looking for external nodes. So we need to have some intuitive way to represent in our pictures and in our minds running into an external node. But that's going to completely change my picture. In fact, it's going to completely change it so much that I'm going to do these cases all over again. But in case you want to split between cases of the cases, I'm going to cut this off where it is and then pick up. It should probably be video 24.2, but I'm not going to do that. I'll see you online.